of two linear equations in two variables can be visually represented by simultaneously graphing both equations. We have also seen that the solutions to these systems fall into three categories depending upon how the two lines in the graph intersect. If the lines intersect at a single point, the system has a single unique solution which corresponds to that point. A system composed of two distinct parallel lines has no solutions, since distinct parallel lines don't intersect. And a system composed of two identical lines has an infinite number of solutions, since identical lines intersect at an infinite number of points. These three types of systems are characterized by two attributes. The systems can be either consistent or inconsistent, and the equations in the system can be either dependent or independent. Systems which have no solutions are said to be inconsistent, and systems with one or more solutions are called consistent, having either one solution or an infinite number of solutions. We can distinguish between these two types of consistent systems by their equations. If the consistent system is composed of two distinct lines, the equations are independent. And if the consistent system is composed of two identical lines, the equations are dependent. Last lecture, we saw that the type of solutions we should expect can be determined when the equations of the system are written in slope-intercept form. In this lecture, we will see how to interpret the results we get when solving the system to tell if the system has one solution, an infinite number of solutions, or no solutions. In the lectures so far, we have seen how to solve systems of equations which consist of two distinct intersecting lines. Using either the substitution or elimination method, we end up with a pair of values for x and y, which is the single unique solution for the system. The system is therefore a consistent system of independent equations. The solution set of this system contains the single-ordered pair 2, 4. Now let's see what happens when we attempt to solve a system of equations composed of two distinct parallel lines. Let's modify the equation used in the last example by changing negative x in the bottom equation to positive x, which changes that equation's graph so that the two lines are now parallel. Using the elimination method to solve this system, we first multiply the bottom equation by -1, and then add the two equations to eliminate a variable. But when we eliminate one variable, both variables are eliminated, and we get the equation 0 = 4. A statement which can never be true, like this statement of equality between two non-equal numbers, is called a contradiction. Obtaining a contradiction when solving a system of equations tells us that the system has no solutions and is therefore inconsistent. Attempting to solve this system by the substitution method will also produce a contradiction. Solving the bottom equation for x, we get x = 2 minus y, which can then be substituted for x in the top equation, producing an equation with only the variable y. The two y terms then cancel, leaving us with the contradiction 2 = 6. Once again, obtaining a contradiction indicates that this system has no solutions and is therefore inconsistent. Since the system has no solutions, its solution set is the empty set. Now let's see what happens when solving a system of equations composed of two identical lines. This time, we'll make one equation a multiple of the other equation so that the two graphs are identical. Using the elimination method to solve this system, we can eliminate a variable by multiplying the bottom equation by -1/2 and then add the two equations. But when we eliminate one variable, every term is eliminated, producing the equation 0 = 0. Obtaining an equation which always must be true, like this statement of equality between two equal numbers, indicates that the equations of the system are dependent, and the system is therefore consistent with an infinite number of solutions. Solving this system by the substitution method will also produce a statement of equality between two equal numbers. We first solve the bottom equation for x by multiplying both sides by 1/2 and then subtracting y from both sides. We can then replace x in the top equation with the result, producing an equation with only the variable y. The two y terms then cancel, leaving us with the statement 6 = 6. Once again, obtaining a statement of equality between two equal numbers indicates that the equations are dependent. The system, therefore, is consistent with an infinite number of solutions.